Welcome you all. I am Shreenath, faculty from Mechanical Department, Canara Engineering College, Mangaluru. On this session, I will explain about topics, that is velocity and acceleration. These topics are connected to fluid mechanics of module number 2. So next, what is velocity and acceleration? So let V is the resultant velocity at any point in a fluid flow. Let U, V and W are its components in X, Y and Z directions. That means here U, V, W are the velocity components in X, Y and Z directions. That is for the three coordinates are taken into consideration here. The velocity components are function of space coordinates and time. So mathematically, the velocity components are given as the U. So U is equals to velocity component in X direction. So here the velocity components are functions of space coordinates as well as time. For that reason, the U is equals to function of, that is f of 1 x, y, z. So these x, y, z are space coordinates and t represents time. So for that reason, the velocity components are the functions of space coordinates and time. Similarly, v is equals to the function of x, y, z and t, and w is equals to the function of x, y, z and function of time. And resultant velocity v is equals to u of I plus v of j plus wk. So that is equals to square root of u square plus v square plus w square. So let a of x, a of y and a of z are the total acceleration in x, y and z directions. So we know that the acceleration is a rate of change of velocity in x, y and z directions. So then by the chain rule of differentiation, we have the a of x, that is acceleration in the direction of x, is equals to change in velocity in x direction or with the respect to time, that means du by dt is equals to, so dou u by dou x dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt plus dou u by dou t. In that last term, dou u by dou t, so that represents the velocity acceleration, also given by the change of velocity with respect to time. But the dx by dt is equals to u. Similarly, dy by dt is equals to v and dz by dt is equals to w. Therefore, the a of x is equals to du by dt is equals to u into dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Similarly, in y directions, that is acceleration in y direction is given by a of y is equals to dv by dt is equals to u into dou v by dou x plus v into dou v by dou y plus w dou v by dou z plus dou v by dou t, and the direction of z, a of z is equals to dw by dt is equals to u into dou w by dou x plus v into dou w by dou y plus w dou w by dou z plus dou w by dou t. So these are the expressions for acceleration in three different directions by the by chain rule of differentiation. So for steady flow, we already discussed in some other topics. For steady flow, dou v by dou t is equals to 0. So where v is the resultant velocity, or dou u by dou t is equals to 0, dou v by dou t is equals to 0, and dou w by dou t is equals to 0. That means the velocity, there is a change in velocity with respect to time is equals to 0 for steady flow. Hence, acceleration in x, y and z directions becomes a of x is equals to du by dt is equals to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So there is no last term, that is dou u by dou t. So because of steady flow, a of y, the acceleration y direction, that is dv by dz is equals to u into dou v by dou x plus dou v by dou y plus w into dou v by dou z. A of z is equals to dw by dt is equals to u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z. So these are the three expressions for acceleration in three different directions for steady flow. Now acceleration vector is given by, that is a is equals to a of x I plus a of y j plus a of z k. So therefore now acceleration vector a is equals to a square root of ax square, a of y square plus a of z square. So next two terms connected to acceleration, so that is a local acceleration as well as a convective acceleration. Local acceleration is defined as the rate of increase of velocity with respect to time at a given point in the flow field. The local acceleration is defined as rate of increase of velocity with respect to time. So here one particular point is considered in a flow field, and with respect to time, so what is the change in velocity or increase in velocity is measured. So that is called as local acceleration. So that is a of x is equals to du by dt. So that is equals to u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. So that is the general expression for acceleration in the direction of x by considering the space coordinates as well as function of time. In similar manner, in the a of y, there is a y direction, that is a dv by dt is equals to u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z plus dou v by dou t, and in the direction of z, that is equals to dw by dt is equals to u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z plus dou w by dou t. So in this one, see, according to the local acceleration, say it is defined the rate of increase of velocity with respect to time. So in this acceleration equation, after the chain rule of differentiation, the last term in each expression, that is d dou u by dt, dou v by dt, and dou w by dou t. So that represents the increase in velocity with respect to time. So now expression dou u by dou t, dou v by dou t, and dou w by dou t is known as local acceleration. Next, convective acceleration. So convective acceleration is defined as the rate of change of velocity due to change of position of fluid particles in a fluid flow. So in this acceleration expression, a of x is equals to du by dt. So that is the u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z plus dou u by dou t. So that is the general expression for the acceleration in x direction and in y direction, as well as similarly in z direction. So in this expression, so here u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. So that represents a change in velocity with respect to position of the fluid particles. Correct. The x, y, z. So that represents the position of the fluid particles. And what is the change in velocity? So that is called as convective acceleration. So similarly in the a of y, the direction of y, so this is a convective acceleration, and in the direction of z, and this term is convective acceleration. So that means the other than dou u by dou t, dou v by dou t, and dou w by dou t terms are called as convective acceleration. The expressions other than dou u by dou t, dou v by dou t, and dou w by dou t are known as convective acceleration. So these are the two terms connected to acceleration, that is convective acceleration as well as local acceleration. The next term related to velocity, so that is a velocity potential function and stream function. The first term in that one, there is a velocity potential function. So it is defined as a scalar function of space and time such that its negative derivative with respect to any direction gives the fluid velocity in that direction. So it is represented by symbol phi. So mathematically, velocity potential is defined as the function of x, y, and z for steady flow, such that the u is equals to minus dou phi by dou x. So here the u represents velocity component in x direction. So then, so according to the definition of the velocity potential function, so it is a scalar function of space as well as time. So that is a negative derivative with respect to any direction. So this is a negative derivative with respect to any direction. So here the negative derivative, for that reason, this part it is u is given as minus dou phi by dou x. Similarly, v is equals to minus dou phi by dou y, and the velocity component in z direction W is equals to minus dou phi by dou Z. So these are the expressions connected to this velocity potential function. So where u, v and w are the velocity components of velocity in x, y and z direction respectively. The continuity equation for an incompressible steady flow is, so dou u by dou x plus dou v by dou y plus dou w by dou z is equals to 0. So already we discussed in some other lecture regarding to this continuity equation. So substituting the values of u, v and w, so we get, so now dou u by dou x, this is the first term in that continuity equation, that is dou u by dou x. So now already we got the expression for u here, the velocity component in x direction, the u is equals to minus dou phi by dou x. So now substitute, so instead of u we have to substitute the velocity potential function. So now this equation becomes dou by dou x into minus dou phi by dou x plus dou by dou y. Then instead of v, you have to substitute minus dou phi by dou y plus dou by dou z, and instead of w, the velocity component w, that is minus dou phi by dou z is equals to 0. After simplification of this one, the dou by dou x, that is multiplied with minus dou phi by dou x. So for that reason it is now dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square. So that is equals to 0. So that is a negative sign is taken common outside and taken to right hand side, that will get cancelled. For that reason it is a positive term here. So this equation is called as Laplace equation. So dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equals to 0 is known as Laplace equation. So for 2D case, for two-dimensional flow, the equation reduces to dou square phi by dou x square plus dou square phi by dou y square is equals to 0. If velocity potential satisfies the Laplace equation, it represents the possible steady, incompressible, irrotational flow. So in case any fluid flow, so that satisfies this Laplace equation. So such type of fluid flow is known as the steady, incompressible, irrotational flow. Stream function. The stream function is defined as the scalar function of space and time such that its partial derivative with respect to any direction gives the velocity component at right angles to that direction. So once again, this is a function of space as well as a time. See here, say the partial derivative with the any directions of the velocity component, and it should be in right angles to that direction now. So it is defined by the symbol xi and defined only for two-dimensional flow. Mathematically, for a steady flow, it is defined as dou xi by dou x is equals to, so there is a the stream function that is defined as a function of x and y. There is a two-dimensional flow. With respect to that, dou phi by dou x is equals to v and dou phi by dou y is equals to minus u. The continuity equation for two-dimensional flow is dou u by dou x plus dou v by dou y is equals to 0. So substitute the values of this u and v in this continuity equation. So now this equation becomes dou by dou x into minus dou phi by dou y plus dou phi by dou y into dou xi by dou x is equals to 0, or dou square xi by dou x into dou y plus dou square xi by dou x into dou y is equals to 0. So this is the expression for stream function. So next, what are the properties of this stream function? If stream function exists, it is a possible case of fluid flow which may be rotational or irrotational. If the stream function satisfies the Laplace equation, it is a possible case of an irrotational flow. So these are the two properties of this stream function. So move on to next term connected to this fluid kinematics, that is equipotential potential line. A line along which the velocity potential is constant is called equipotential potential line. So that is equipotential is equals to constant. That is dou phi is equals to 0, but phi is equals to function of x and y for steady flow. Therefore, dou phi is equals to dou phi by dou x into dx plus dou phi by dou y into dy. Therefore, minus u into dx minus v into dy. So because dou phi by dou x is equals to minus u and dou phi by dou y is equals to minus v. With respect to that, if it negative sign is taken common outside, then u into dx plus v into dy. So for equipotential line, dou phi is equals to 0. So now this equation becomes 0 is equals to minus u into dx plus v into dy. So finally it is get simplified, and then dy by dx is equals to minus u by v. That is expression number taken as a. Dou y by dou x is equals to slope of equipotential line. So in this expression, the dou y by dou x is equals to slope of equipotential line. It's a line of constant stream function. Xi is equals to constant, that is a d xi is equals to 0. So now d xi is equals to dou xi by dou x into dx plus dou xi by dou y into dy. So that is equals to v into dx minus u into dy. So because we already know that the dou xi by dou x is equals to v, dou xi by dou y is equals to minus u. So for a line of constant stream function, dou xi is equals to constant 0, that is equals to 0 is equals to v dx minus u dy, or dou y by dou x is equals to v by u. So that is the second expression b. But dy by dx is a slope of stream line. For equations a and b, the product of slope of the equipotential line and slope of streamline at the point of intersection is equals to minus 1. Thus, equipotential lines are orthogonal to streamlines at all points of intersection. So next term, flow net. A grid obtained by drawing a series of equipotential lines and streamlines is called a flow net. After calculating there is values for the equipotential lines as well as streamlines. So now it is shown like that. So it is an important tool in analyzing two-dimensional irrotational flow pattern. So this is a flow net. So here on this diagram we can see the series of equipotential lines as well as a series of streamlines, and the intersection is taking place at one point here. So now relationship between stream function and velocity potential function. So we have u is equals to dou phi by dou x and v is equals to minus dou phi by dou y. Also we have the u is equals to, according to the stream functions, minus dou phi by dou y, and v is equals to dou xi by dou x. So thus we have u is equals to minus dou phi by dou x, so that is equals to minus dou phi by dou xi by dou y. Similarly for v is equals to minus dou phi by dou y, so that is equals to dou xi by dou x. Hence dou phi by dou x is equals to dou xi by dou y. So that is the relation between stream function as well as velocity function. And as well as the one more expression, dou phi by dou y is equals to minus dou xi by dou x. Next, streamlines. The fluid motion can be quite complicated. So there are various concepts that can be used to help in the visualization and analysis of flow fields. The streamline is often used in analytical work, while the streakline and pathline are often used in experimental work. A streamline is a line. Streamline is a line so that is everywhere tangent to the velocity field. If the flow is steady at a fixed point and changes with the time, so the streamlines are fixed lines in a space. So here it shows the streamline of fluid flowing over the aerofoil shape, and we can also see the disturbance or the turbulence after the separation point. So here clearly we can see the disturbance or the turbulence flow in a flow field, and here the position will also taken into consideration for the formation of the turbulent flow. So once again here we can see some analysis of fluid flow. So while taking the drive on a vehicle and back side of the vehicle, we can see there is a separation point, and also we can observe the turbulence occurring, and here also we can see the flow of fluid. Next, coming to streakline. The streakline consists of all particles in a flow so that have previously passed through the common point, and streaklines are more of laboratory tool than the analytical tool. The streak line is the locus of the temporary locations of all particles so that have passed through a fixed point in the flow field at any instant of time. So this is obtained by taking instantaneous photos of the marked particles that are passed through the given location in a flow field at some earlier time. The third method used for visualizing and describing flows involves the use of path lines. The path line is the line traced out by the given particles as it flows from one point to the another. That means what is the path followed by the fluid particles while it is traveled from one point to the another point. A path line is the trajectory of the fluid particles of mixed identity. So here we can see the path followed by the different fluid particles here, that is 1, 2, 3, 4, that represents the 4 different fluid particles, and P represents the path followed by these 4 different fluid particles. Next, what is the difference between path line as well as streamline? The path line, so this refers to a path followed by a fluid particle over a period of time. But streamline, this is an imaginary curve in flow field for a fixed instant of time. There is a tangent which gives the instantaneous velocity at that point. In path line, the two path lines can intersect each other, or as or when a single path line can form a loop as different particles, or even some particle can arrive at the same point at different instant of time. The two streamlines can never intersect each other as the instantaneous velocity vector at any given point is unique. In this section, we have discussed about velocity and acceleration and some other terms connected to acceleration, that is local acceleration and convective acceleration. We also discussed about the stream function, velocity potential function, streak lines, streamlines, as well as path lines. So also we got some relations connected to stream function as well as potential velocity potential function. What are the relations between these stream function, then velocity potential function? Thank you.